So welcome all to the 16th lecture of Statistical Learning in Practice. We're going to cover, as I was just saying, artificial neural networks. So let me start. Artificial neural networks. And as you can imagine, they are related to the brain's neural networks. So originally they wanted to model the way in which neurons were connected, and so you were trying to replicate the brain by having this kind of model. And at the same time, they were a subclass of some algorithms that were being used, several decades ago. Okay, so let's go into the model, and we're going to cover basically the most well-known type of neural network, and also the one that is easiest in terms of potential complications in its training and so on. So before that, let me start, or seemingly start, a bit more general and say the following. So artificial neural networks are a multi-step classification, but also, let me say that they are used for regression just as much. Well, yeah, I mean, just as well. So there are, the previous classifiers that I was talking about are, generally used for classification, except perhaps logistic regression, and they are built, sort of explicitly to account for different classes, but that's not the case for artificial neural networks. Yeah? And regression. Models. And then a very characteristic thing about them is that they have an architecture and this one is depicted by a directed graph. Okay, so let me give you an example so that we're on the same page. Okay, so we're going to begin with writing the nodes that we have. So this is x1 not, x2 not, and so on, up to x p naught. So that's the dimension of this, so to say, column, which is not really a column, we'll see now. And here we're going to have, same guy, but now for the first, so for the first column rather than zeroth, x2 of the first, so on, to xp1. So these, even though I'm aligning them, they may not have the same size. And then we're going to go all the way up to some xp1, sorry, not xp1, x1. This is for capital H, x2 and capital H, up to x p h h, and then x1 at h plus 1, x2 h plus 1, h plus 1, h plus 1. Okay? Okay, so I said these are nodes, so let's just draw some circles around them. And in the context of neural networks, they're going to also be called units or neurons. Yeah. Okay, so let's say that. Actually, let me, before writing that, let me say that. I mean, we said this is a graph, and not only a graph, so we need vertices now, but also directed vertices. Yeah. So let's imagine, that this one's connected to that, this one's connected to this one, then maybe this one's connected to that one, and it's directed. So this is why I'm writing arrows. Then maybe this one's connected to that one, and maybe these have several connections. Okay, so we have here, more nodes, and then we connect these. So imagine now that okay. So I said that these guys are nodes. These are nodes, units, neurons. Okay, and okay, and this would give you the directed graph, and we're going to give different names. So because we now have these directions, then we see that we can classify them into different, these things that I was calling columns, they can be layers as well, right? And so this is the input layer. Okay, this is the output layer. And then the rest of the layers in between are called the hidden layers. Okay. Okay, and in neural networks, there are also additional nodes that in many occasions are not represented, but let me represent them for clarity. So these are going to be X, I'm going to call them X naught naught, X naught 1. So for every layer except for the output layer. Sorry, I want to do something different, which is to dash them precisely to warn you that these, you won't generally see them on, in the usual descriptions or diagrams. Okay, and these also are going to be connected. Generally speaking, they are connected to all. Okay, and again, they are not in the output layer. Okay, so these are, as I'm just saying, these are bias nodes. Bias nodes. Okay, so we'll see what they are for, why they are a bit special. Okay, so now I've cheated a bit because this is not just any directed graph. Okay, so this is as you can see, we cannot create cycles, right, in this one. So this is what is called a directed acyclic graph. Sometimes called DAG. We'll see that DAG in papers. Okay, and so it depicts the architecture of a feed-forward neural network. Okay, so it's not just any artificial neural network. The one I drew up there. So I will call this FNN. Okay. Which are going to be, so these guys are going to be our focus. Okay. So in the practical, I will include a section on convolutional neural networks, which are different from these, and they are used in imaging applications, and they are quite important. So this is why I'm going to include them there, although in a non-examinable, with they're basically non-examinable. Yeah. Okay, so good. So we have some sort of graphical description of a neural network, but we haven't really introduced any model, right? So what is the model? Right, we still need to connect. I mean, we're in classification, so we need to connect the covariates to some estimates of the regressors, right? Okay, so for each unit, and describe, the relationship between the two. So for each unit, x, j, h, and I'm not including the bias nodes. So therefore, we're going to have that j goes from 1 to ph, and h is going to go from 1 to h plus 1. So I'm also not including the input layer. We're going to introduce parameters. Okay, introduce parameters, which in the context of artificial neural networks, they're called weights. Okay, and these are going to be beta j, and there's a vector what I'm introducing here. So let me underline it, or let me actually write it out as well. This is going to be beta j1. Actually, let me write k here, and then I don't need to write it in such a way, but let me start from 0 and not from 1, because we're going to include the bias nodes. So this goes from the previous layer. We'll see this in a sec, it'll be clear. And so this belongs to R1 plus PH minus 1. And let us also writing X underline H as all of the units, and now including the bias nodes and also the input layer, but not the output layer. So I said this would be a bit involved notationally, this lecture. We're going to define, some quantities that we call SJH, okay, which are linear combinations. So this linear combination is the product of this H minus 1 transpose times the beta JH. Okay, so it should be clear what is going on. So this linear combination is the product of the x's coming from the previous layer. So let's imagine that we're in some, let's say that we're in the first layer here. Then what we have is that we have the linear combination of all of the guys, including the bias nodes of the input layer, and then with some coefficients beta that of course have have as many elements as the unit, as the input layer, right? Okay, and this, we work it out for any units that are not the bias unit, okay? Right, and so let me just say graphically, so define this, and let me just point out, so in particular, beta jkh being 0 is going to be depicted by no edge from xkh minus 1 to xjh, right? That should be clear. Okay, so we kill them with this beta coefficient being 0, right? Okay, so still we don't have the model, but at least we have parameters. So let's now introduce the model, but to introduce it, we need some assumptions. So then let's take x naught h to be 1. So these are the bias nodes, okay? And this is for all h from 0 to capital H, so all the bias nodes. And then we're going to take p naught, so the size of the input layer, to be the usual p that we have. And we're going to take actually, the input layers, units to be exactly the covariates, so not including the bias node, of course. And this is for J1 to P naught. Remember, P naught is now P. And also let me take PH plus 1, so the size of the output layer, to be this capital L that we have, which is the number of classes or categories. So then if all this happens, we're going to model the regressors. These guys are modeled via x h plus 1. Okay, so remember that before so up here we have we have defined this vector so that we could use the linear combinations using the previous layer. And so it wasn't, the x's or the units from the output layer were not included in here. So we need to define this guy and this guy. The only difference with the above is that we don't take that would be h plus 1. We don't take the bias because there is no bias in that layer, right? Okay, so via this, but we're still missing something, right? So we need to connect the different layers in some analytic way. And so we do that in this way. So we have xjh plus 1 to be, so this is the output, remember? So it's going to be, for each j, we're going to have a function fj that is going to depend on the linear combinations for those output units. And this is actually capital L, this pH plus 1, but I'll just stick to this. And also, now what about the previous nodes? Well, the previous nodes have the same function of the linear combinations for a given layer. Okay, so they share you could make this not share what is going to be called, so this is an activation function, the GH, but it's the common thing is to have the same for every element in a given layer. Excuse me, this is not full stop because, as I just said, so we need to say what these functions are. So this is where this for some, so let me call output functions or rules f1 to f ph plus 1 and some activation functions or rules G1 to G capital H. Yeah. Okay, so, and by the way, the indices, the J here and the J and the lowercase h here run through different, slightly different numbers, but that should be clear. So, you know, everything is well defined beforehand. So I'll let you think about those things. Yeah? So there should be no room for confusion. Okay, in terms of indices. Okay, so what did I say? Well, let me just recap a bit, because this is, as I said, a bit notationally involved. What we are going to have is, so the etas, we're going to model them via the quantities that we will get in the output layer. Okay, so these guys here, these are the guys that will give us the final sort of estimate of the probabilities, and those guys are computed from the linear combinations that we assign to the units, and we do so via so-called output, an output rule that may be different for every element. Actually, will be different in terms for classification. And before that, we will get the value of each of the units, the previous layers, via a function called an activation function of the linear combination of the previous units. Okay. Okay, so we have this, as I started the lecture with, as a multi-step function of the input. Okay, so really, I mean, there is no need here to have a neural, you know, to have this diagram, this graph diagram, right? I mean, this is just a composition of functions and full stop. Yeah? But having this network sort of eases the understanding of the model. Yeah. Okay, so let's stick then to classification. So in classification, we have some common choices of these guys. So the common choices are the so-called soft max output function, which is given by, you know, f, j, and if we have capital L of these, this is going to be e to the sj divided by the sum from L equal 1 to capital L, the es L. And by the way, in this case, the problem is that we need to, you know, if you add a constant here and you add the same constant to all of these guys, to all of the s's. So remember, the s's are a linear combination, so they have this bias node. So if you added the same constant, then you would, they would cancel out here. So we need to, so that would mean we have identifiability issues. So one needs to assume this guy, you know, the one of them is 0 by convention. So this should be very familiar from logistic regression, and we'll see why. So they're very connected, these guys. And then for the activation function, we have the sigmoid, or also called expert or logistic activation rule, which is given by g of s equal to e to the s 1 plus e to the s. Or another one is, or the rectifier or ReLU activation rule given by the positive part of S. So this is the max between S and 0. Okay. All right. So we now really have all the model. Yeah. So we've defined the model fully. And now, therefore, we want to train it, right? So how do we train? How to train the feed-forward neural network from data x1, excuse me, y1 to xn, yn. Okay, so let us write theta for all of the parameters. So these are going to be the beta j's h underline, where j is going to go from 1 to ph, and h is going to go from 1 to h plus 1. Okay. So that what we really have is x h plus 1 being a function of not only the input, but also of the theta. Yeah? So we may write it in one way or another, and let L go from RL times RL to R, and there is some abuse of notation here because the capital L means different things. Yeah, so R positive, of course. So the capital L is the number of classes in this case, and then the one in the R's, and then the function itself is a loss function as you're expecting. So let this guy be a loss function, but you should start getting comfortable with this kind of abusive notation sometimes. Okay, so then what we do is to minimize what you expect, yeah, which is the sum. So we call this capital R theta. It's going to be the sum of these guys, the yi, and then the x bar h plus 1. Now this is for theta, right? And xi here. And so I was saying that this is what you expect because we are sort of assuming independence, yeah, here to train it, even though it may not be true. And then in that case, one can try to modify it if possible, but that's not the usual thing, yeah? So the usual thing is just to assume the independence, yeah? Okay, so then we minimize this, and let's give some common choices of the loss function. So if the yi is independent, and in this case, we now assume it as a model, so multinomial with parameters 1 and then some etas, okay, which may not be, of course, let me write here, given xi, eta capital L, xi. Then common choices so we have the negative log likelihood, so that's just a likelihood principle from the likelihood principle, so the negative log likelihood, which, by the way, you won't see being called negative log likelihood in machine learning papers, but well, sometimes you may, but most occasions you'll see this called as the cross entropy loss. And this one's given by the negative L equal 1 to capital L of the indicator of the y L, so the Lth element in this vector of zeros and ones, so it being 1, and then the logarithm of xl. Okay, so that's just the usual negative log likelihood from multinomial model. Yeah, and then the squared error loss, as you can imagine, this is another one that is used. Okay, so Lyx equal to the sum, well, actually, let's write L2 first, minus x to 2, 1 to L of the y L x L squared. Okay. Okay. So now, we have a model analytically, and we have a training, I guess, strategy. And so we can define now the classifier that results from all of this. So definition 16. So let x hat, and this is h plus 1, underline be the trained feed-forward neural network. What do I mean by this? Well, I mean that if theta hat are the parameters say them the fitted parameters, and we don't need to talk about how we fitted them. Then it is given by just the usual, the functions we wrote it above, but for that guy, and it's a function of the x's. Okay. Then the feed-forward neural network classifier is given by the arg max of x, and then the x we're going to write subscript because we're going to choose from all of these guys, and this is over L. Yeah. Okay. Okay, so let's maybe make a little remark. So note the following: a fully, which you may have noticed already, connected. So what do I mean by fully connected? I mean a graph. So let's say I don't want to write that. I was going to write complete graph, but that's not really it. So fully connected network. We go back to our picture, and so it's one in which we have all of the possible arrows. Yeah, but remember that the bias nodes have no predecessors. So we cannot connect the other guys to the bias nodes, but let's imagine that the rest are connected, fully connected. So a fully connected feed-forward neural network with no hidden layers sigmoid and output, sigmoid and softmax activation and output functions that is trained via cross entropy is no more than a logistic classifier. So we see that logistic classification is a special case of feed-forward neural networks. And this is why, we also have this logistic activation function in the terminology. Okay, so let's write a theorem. This is a theorem by Baron, a very popular theorem. So assume, as we've been doing, that the yi's are independent from multinomial distribution. With parameters 1, delta 1. Okay, so maybe we should write given x, x delta 2x. Okay, so I'm talking about a binary class, label, if you like. So with delta 1 and delta 2, let's maybe just anticipate previous, let's call it delta. That goes from so it's going to go, okay, so this delta is going to go from RD, some RD to the simplex, basically in 2 dimensions. So this is going to be the delta 1, delta 2 vectors that are, in the positive or non-negative reals in 2 dimensions, such that the sum is 1. Okay, satisfying some mild regularity assumptions, which I'm not going to go into. If you're interested, you can see the paper, which I will include in the bibliography. So mild regularity assumptions. Then there exists a positive constant and a fully connected feed-forward neural network that is shallow. So what do I mean by shallow? I mean that it only has 1 hidden layer. So let's call this shallow. And in which we take this P capital H to be M, just for simplicity. It has softmax activation, this is an output function, sigmoid activation function. So let's say output and activation functions trained via the negative log likelihood via the squared error loss, such that the L2 norm between the classifier that we've, not the classifier, but the regressors of this data generating mechanism are not, the distance from this model, say, is no more than the following. So we have this constant capital C, and then 1 over m plus m log of p log of n, over n, and this, okay? So by the way, this is the bias, okay, and this is the variance. So generally, that's the case that we have a bias and a variance term. The way to distinguish them, generally is that you have the number of parameters, it takes, the variance will grow with them, because we have the same randomness to estimate more and more parameters. We have less ability to do so well in each of them, and then the bias will decrease as we add more and more parameters, right? Okay, so in particular, and really this theorem is about the bias, so the variance is not hard to show to be this quantity, but the bias was, really the addition of this paper. And in particular, so the usual thing, remember that when we have variance and bias, is that we wish, neither of the two to be small, but rather the sum of them, because we could always make this guy as small as we like, but this one would grow and the other way around. And so really the usual thing in this, with this bias variance trade-off, is to try to take the m that minimizes the sum. And this is here is of order n over p log of n. And so in this case, the left hand side is O of P log n divided by n. Okay. Okay, so what this is saying is that we should probably mention something about the mild regularity assumptions, but these are basically continuity with slight differentiability. And what this is saying is that we can approximate any such data generating mechanism by a shallow network in which we're going to have to take as many, many nodes, or units, which is given by this m. Okay, but when, if we're free to choose as many units as we like, then we can always get this order of error, which is actually decreasing nearly like the inverse of the square root of n, which is essentially the best rate that one can have. So remember, this is the same as in the MLE of regression models that we were seeing. And in this non-parametric world, because this is really, what we're approximating is this deltas, or this delta, which is just, like a continuous function. But in this non-parametric world, the rates are no longer always this inverse of the square root of n, but rather generally slower things, just as here, although here is just a log n slower, Okay, and this theorem actually is what gives the name of or neural networks of universal approximators. So you will see this in many cases, in many places. And actually, this is not very surprising. So generally, we want things that can adapt to even more degrees of regularity. But anyway, that's it's generally is generally referred to this result. Okay, so let's make another remark. So generally, if you wish to or generally, let's say that better to go deep. Yeah. Okay, so now we go into a bit more modern terminologies. So better to go deep. What do I mean by this? M needs to be very large if we wish to attain some accuracy. Better to add layers. Okay, so if we add layers, then we're going to need in total less total number of parameters. Yeah. Okay, that's that. Okay, so now that we are talking about deep, we're talking about sort of more modern things. So in modern applications, the dimension of the parameters and also n are quite large. Yeah. So with generally speaking, actually, the dimension of this guy being much greater than the number of data points, not necessarily, but it can be. And even if it's not, the following is good to be done. So thus, it is common to use some regularization procedures. Yeah. Or common to add. In this case, what we can do is to show a way of regularization. So common to add a penalty term p theta to r theta. Okay, such as the usual ones that we've seen. Yeah? P theta being lambda, and then the Q norm of the parameters, with Q being not 0, 1, excuse me, 1 or 2. Okay, so let me okay, so one sec. Yeah, we need to remove the bias nodes, right? The bias parameters. Yeah. This is theta without bias parameters. Okay, and then due to n being very large, we're going to have to substitute gradient descent by stochastic gradient descent. Okay, so what is stochastic gradient descent? So let me introduce it quickly. So stochastic gradient descent. It's the following. So in this one, so let's go a bit more general. So we wish to minimize f going from Rd to R, okay, which is a differentiable function. And such that it can be written as follows. So as an average of functions. Okay. Then, of course, what we have is that if we take the gradient with respect to this W, this is going to be, you know, the sum of the average of gradients, and we have that the gradient of f is approximately the gradient of each of these guys. Yeah. Why am I saying this? Well, just think of this sum as a Monte Carlo version of, you know, the expectation of each of them, even though that doesn't necessarily make sense at all because there may not be any randomness. But still, you know, think of it that way. And so, of course, one of the elements is an approximation to that average. Yeah. If they were IID. Yeah. Okay. So that's the idea of stochastic gradient descent. So what we're going to do is first, you know, choose an initial guy that is so 0 n, we're going to call it, and this is of course from RD. And then second, we have that for E going from 1 to capital E, which is called the epochs. This is the number of epochs. So E is the number of epochs, and each of them is an epoch. So these are the epochs. A, so A, we're going to set, we wish to know where to start in each epoch. So we write the first element in the epoch as the last element of the previous epoch. Then B, we're going to have, and generally, this is generally done, not always, but these are just exceptions, absolute exceptions in which we may not want to do the following. So let me just write, forget about generally. I mean, it's just nearly always done. So randomly reorder indices 1 to n, and C set, you know, this guy that we're looking at as the previous guy minus, because we're minimizing, this is called the learning rate, alpha subscript E, the gradient of this guy at the previous value. And this is, of course, for every I going from 1 to n, and these are reordered indices. Okay. So I would have liked to make a few remarks, but these, I will include them in the notes, you know, that we have convergence. Then the other thing that maybe I wish to say is that, you know, in a slightly more detail, is that as you see, rather than having an average as we would have had in gradient descent, here we just use one element. So we are really just moving probably, you know, smaller amounts, but we are moving many more times for the same cost or for very similar costs, right? So if we looked at a single epoch, then we've computed the same number of gradients as in the whole of gradient descent, and only one step of gradient descent, while here we give n steps. So what will happen is that we are sort of moving in similar direction as gradient descent would give us, but, you know, in smaller, sort of more or less aligned steps. Yeah, so this is why it's called stochastic gradient descent, because we just sort of taking the space a bit more in a bit more wiggly fashion. Yeah, and also taking small number of epochs serves as a regularization procedure. Okay, so you can read the remarks in the notes, but let me just for terminology say that we also have an intermediate, I guess, training algorithm between gradient descent and stochastic gradient descent, which is called Minipad gradient descent. And so let capital K be 1n, not including either of them, and such that n over this capital K is in the natural numbers. And we swap to C by the following, which is rather than having I, we now have K. So we look at the previous one and we subtract, we're still writing the same quantities. Sorry, oh, of course not. So we have an average now of a few of them, yeah? And this is from I K minus 1 is 1 n over K, some K. And we have these guys here, just the same guys. Yeah? And this is for K going from 1 to capital K. And let me just, for terminology, say that SGD is also known as vanilla SGD. And gradient descent is also known as BAT SGD. Okay. All right. So apologies, I've gone a bit over the time. But this ends the lecture. I can stay for a couple of minutes if anyone has any questions.
I've got a question about
yeah.
When you said you drew the parallel of the logistic regression classifier as a neural network with no hidden layers.
Yeah.
You said it had sigmoid activation, but I thought activation was only about hidden layers.
No, because you still let me just think for a sec. Yeah, you're right. Yeah,
Thanks.
right. Yeah, I didn't have to write that. I mean, it's not wrong because it's not applied to anything, but you're totally right. Yes. I'm joking, of course. Yeah. Yeah. Let me say here, sigmoid. Let me cross it. Okay. Any more questions?